All right, good morning, everybody. Let's see. Perfect. All righty. Um, so yeah, so if you came in just like in the last couple of minutes, you might have missed the thing that I put in the chart or the chat about two additional problems on the problem list document on Canvas. So we'll go over, I just added a couple just so we'd have lots and lots of practice before your test on Monday. So we'll have 5 conceptual questions. Those are going to be multiple choice questions, should be pretty easy to wrap up very quickly. And then just one open-ended question because it really is, it's a short amount of time that you have. It's only 50 minutes and it goes by really quickly. So I will be there. I don't think there's a class before us. I think they were the first class that day. I could be wrong. So let's see. Yeah, so I plan on being there like about, 10 minutes before class starts. And as soon as you come in, I'll just give you the test. So I try to give you as much time as I can. But of course, once the next class comes in, we need to skedaddle. Um, all you need to bring is something to write with, a non-programmable calculator, something that's allowed on the FE exam. Oh, I'm sorry. Yeah, 5 multiple choice questions, 1 open-ended question. And then I'll provide that PDF. I'll have it printed out. Hopefully the printer's going now. I printed it off from home, so I'm going to go see if everything printed off correctly in a little bit. But the entire printed PDF of those thermodynamic tables and the equation sheet, and we'll just reuse those every time we've got a test. Then, of course, the testing booklet and any extra paper. So everything that's on that PDF, you'll have access to. The tables, the table of contents, the equation sheet, all that stuff you've got. So if you haven't, make sure that you scan your work. To a PDF. I would practice using that exam upload and submission example. Just make sure it all works okay. If I've got like 1 or 2 people that have trouble, then that's no big deal. I can handle that. But trying to handle 40 uploads myself is going to be very cumbersome. So that's why I'm asking you if you please do that. So you'll hand me your hard copy, but you'll also scan your work up to the Unit 1 or the Exam 1 placeholder, I guess. And as far as what you should expect, any of the problems that we've done in class, any of the problems that you saw on the practice exam, all that stuff is fair game. And you probably want to focus on the ones that have a process involved. So from like state 1 to state 2, it's unlikely that I would just say, okay, give me the specific volume of water at this particular state. Now I'll be looking for a particular process. Be prepared for, TV and or a PV diagram, that kind of thing. Okay. All right, so problem 19, that's where we got last time. So we've got a 2-phase liquid vapor mixture of water at 200 psi with a quality of 80%. The mixture is heated and expands at constant pressure until a final temperature of 480 degrees is reached. Determine the change in specific volume and draw the process on a PV diagram. And I guess that's the only thing I didn't, oh, no, it's right there, PV diagram. Also be prepared to fill out that given, find, assume stuff yourself, right? So I would make sure that you copy or you cover that stuff up when you solve or when you go back and solve the problems. Copy that, make sure that you can find those important elements of the problem in your given. All right, so for your change in specific volume, obviously you're going to need to know the specific volume V1 and V2. So for state 1, it's saturated, right? Because, oops, is that not? There we go. Because our P1 is 200 psi, and our quality is 0.8. I put P2 is 200 psi over here just while I've got it. And T2 is 480 degrees Fahrenheit. So always, 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 you're trying to figure out, what 2 independent intensive properties do I know? Which one of those well, which two of those do I know of those four properties? You're going to need those to fix your state. So for state one, obviously it's saturated because you've got a quality. Quality is not defined in the compressed region or the superheated region. It's only defined in the saturated region. So, for example, if you were asked, what's the quality of a superheated vapor, you would say it doesn't have one because it's not defined there. Same thing for the compressed region. All right, oopsies. All right, so at 200 psi, and you'll notice that we're in those English unit tables, so do pay attention to that. See that we've got a V sub F and a V sub G value. So your V1, it's going to be sub F plus your quality times your V sub G minus V sub F. So I've got 0.01839. This is all in feet cubed per pound mass. So I'm going to put the feet cubed per pound mass on the outside. 2.289 minus 0.01839. That's going to be in feet cubed per pound mass. So I get a V1 of, let's see, 1.835. And that is in feet cubed per pound mass. Perfect. And I think that's really all I need to know, because that was my, I needed for part A, of course, I need V1 and V2, but I also need V1 and V2 for the PV diagram, and I've got the pressure, so I think I'm good there. Obviously, if I wanted to know the temperature, it's just the saturation temperature at state 1. All right, so now we got state 2. So we're given the pressure and the temperature, and if I go to those saturated tables, which is where you're always going to go to fix your state, at 200 degrees Celsius, you could see that your saturation temperature is 381.86 degrees Fahrenheit, and so RT2 is greater than that, and so you know that it is superheated. So this is T-sat at 200 psi. All right, so it's superheated. So you do need to go to those superheated tables. And so all we need to do is go find the box that corresponds to that 200 psi. Didn't actually get my, let's see which one it is. Notice that what the problem that I've got here is I don't actually have the temperature on there, so I've got to fill in that data here. So let's see, 200 psi. So let's do that. This is the saturation temperature. We're at 480. So this is 400 degrees. This is 450. And this is 500. And I guess it doesn't really matter what the other ones are. The only one that we need is 480. And the problem is, of course, he's not on the table, but that's okay, because we can just interpolate. This right here, whatever that value is, that's going to be my V2. So of course we've got to interpolate. And if you do that, I get a specific volume of 2.654. That's going to be in feet cubed per pound mass as well. Okay. All right, so we fixed our state. And so for part A, of course, I've got my delta specific volume. Let's make that again. So your delta, it's whatever it is after minus what it is before. So, 2.654 minus that 1.835 number, heat cubed per pound mass. Right. So whatever that is. All right. So plug and chug, that's fine. I mean, honestly, if you wrote that, that's full credit for me. All right, so now we got our PV diagram. So go. And this is so simple because it's let's add a TV diagram because it just seems so stupid to have just the TV diagram for this constant pressure process, or just the PV diagram for that constant pressure process. So you start out obviously in that two-phase region, and then constant pressure process out to the superheated region. So that's pretty easy. All I'm going to do here, I'm going to put V2 and I'm going to put V1 because I've got those defined elsewhere, and that's perfectly fine. And then I could put 200 PSI here. As long as everything is defined, that's really what I'm looking for. And then for our TV diagram, I don't know why I didn't have this on there. So it's a constant pressure process. So I would start by just kind of drawing yourself a little line of constant pressure here. Got somewhere in that two-phase region, probably a little bit closer to the saturated vapor line, but that's fine. So this is 1, and then you're out in the superheated region, and it goes along a line of constant pressure. So it needs to be pretty obvious that it's going straight across in the two-phase region, and then it goes up. Once again, here's my V1. Here's my V2. I guess I would need my temperature here. So this is 480 degrees Fahrenheit. And then that T1, I'd mentioned it, like if we need it. I guess we're going to say we need it. So it's the T-sat at P1, so 381.86. So
I have a question.
Yeah.
Why doesn't on the PV diagram your red line follow a line of constant temperature and go down, but on the TV it goes up?
Because you're overthinking it. It's a constant pressure process, right? So it's going to take it's going to take place along a line of constant pressure. So on the PV diagram, it's just going to go straight across, right?
Okay.
Yeah.
Okay. I got you.
Yep.
Thank you.
Yep. All right. So there we go. So keep in mind, to get full credit, you need to label your T1, P1, V1, V2, and define it somewhere on there. If it's not defined in the text of the problem, make sure you define it on the actual figure itself. Like, give me that number, and make sure that you draw it along the appropriate line, right? If it's constant pressure process, draw it along a line of constant pressure. Same thing, constant temperature process, constant volume process, along a line of constant volume. All right, so problem 20.
Professor?
Yes?
Would you mind going over the interpolation? I was getting a number a little bit different from what you had.
So for the interpolation, let's go over here real quick. All right. So for that interpolation, you'd have, let's see. So I would say, oops, I'm sorry. It's a little bit skinnier.
Oh, actually, I think I see. I wrote 486 and not 480.
Okay.
Thank you. Yep.
Yeah. Yeah, but at 200, basically, this is your chart right here, right? All right. So problem 20, we got 1 kilogram of water. So kilogram of water initially at the critical point. And so I showed you where to find that information before. You can find it at table A1, which lists the critical temperature and critical pressure for various substances, including water. But you can also find it like at the very end of your saturated table. So the very end of table A2 for the critical temperature, and the end of A3 for critical pressure. So let's look at that real quick. So we're looking at the critical temperature and pressure. So we want the critical temperature and pressure. All right. So at the very bottom of table A2, that's this guy right here. And you can see you've also got the critical pressure right there. That's the same thing over here. So it's that very last data point, but there's another place you can get it. It's in table A1, although it's in Kelvin as opposed to degrees Celsius. But I just want to show you there are two places to get that information. So I'm going to actually write that in my givens just to kind of keep everything straight. So critical pressure is 220.9 bar. Critical temperature is 220.9. I'm sorry, just said that. 374.14. And then I've got this specific volume here. So remember the critical temperature and critical pressure, the critical point, I'm just going to draw it on a TV diagram. It's like right here. That's where it is. And so, you know I've got like a V sub F and V sub G value, but there's only one location that could be at. And you'll see that this and this are the same number because that guy's already been multiplied by 1,000. Right? Oh, I'm sorry. This and this, apologies. This and this. Boop. Boop. Right, so there's only one possible specific volume that it could be at, and that would be 0.003155. 0.00, what's it? 3155. All right, so now that we've sort of got that out of the way, so it's at the critical point. If the water is cooled at a constant specific volume to a pressure of 30 bar, and I know it says specific volume, just keep in mind, this is, if I didn't say specific, it's constant volume because we're talking about a control mass, a closed system, a chunk of mass. So it's same mass, same volume, so it's the same specific volume. To a final pressure of 30 bar. Okay, so that's case A. We want to find the quality at the final state. And then we also want to draw it on a TV diagram. But then we also want to look at, well, what if it was a constant temperature process? So same thing, but we want to find the specific volume. And we're going to draw both of those on a TV diagram. So let's go ahead and take care of those guys. All right. So case A, constant volume. Well, so at state 2, you'd have P2 is 30 bar, and your V2 is that 0.003155 meters cubed per kilogram. So go into our saturated tables because we need to figure out what phase we're in. So I'm going to table A3, and at 30 bar, it looks like if we're between 0.0012165 and 0.06 and change, then it's saturated. So clearly, that's what we've got. It's saturated. Okay. So that means that V2 follows this little formula, V sub F plus our quality times V sub G minus V sub F. And you're using this value and this value. Just make sure that you multiply, or it's not 1.2 and change, it's 0.0012 and change for that V sub F value. And so all you're doing is rearranging this. So this is V2 minus your V sub F over V sub G minus V sub F. I've got 0.0296 for our quality. And then if I wanted to draw it on a TV diagram, okay. So clearly state 1 is up here at the top. This is my 374.14 degrees Celsius. And then state 2, oh, the only possible temperature that you could be at and be saturated at 30 bar would be 233.9 degrees Celsius. So let's put that guy right there. Zoop. And I guess the only other thing that I might do is put, this is my V1, which is the same as V2. And as long as I've got it defined somewhere on my work, that's fine with me. As long as it's pretty obvious that that's what it is, I'm good. Okay. So that's case A. And case B was if we had a constant temperature process. So this is a little bit strange, but this is a constant temperature process to 30 bar. So this guy, we're saying P2 is 30 bar, but your T2 is equal to T1, where that T1 was 374.14. Yeah. All right. So you could look here, oops, I'm sorry. Here you could look at table A2 or A3. So you could look at table A3 or A2. So if you look at table A3, you're looking up things by pressure, and you should see that your saturation temperature at 30 bar is less than that 374.14, so it would tell you were superheated. Or you could look in table A2. It doesn't really matter, same information. So you could see, well, at 374.14 degrees Celsius, which is what I am at state 2, it would have to be at a pressure of 220.9 bar in order for me to get the information I needed off of those saturated tables. And of course my pressure is at 30 bar, which is less than that. So I know it's superheated. Right? What does that mean, or why? So you could, based on table A2, that's because your pressure P2 is less than this saturation pressure at T2, or you could figure out that T2 is greater than Tsat at P2. And you would get that in table A3. So either one is going to give you the same information. So I'm going to go to my superheated tables at 30 bar. It's a little bit annoying because I do have to interpolate. My temperature is not actually on there, but I got 374.14 degrees Celsius. And so if I interpolate, which I'm going to do right now, then I would get a specific V2 that's between those two values. So I should get 0.0948. Okay, it does. 0.0948 meters cubed per kilogram. And so that was, of course, one of the things that I was supposed to find, but I was also supposed to draw things on a TV diagram. So I'm going to do that as well. So state 1 for case B, still starting up at that critical point, but it's going to be a constant temperature process out to that superheated region. Right, so this is 374.14 degrees Celsius. Here's my V1. I've defined that elsewhere. Here's my V2. I just defined it right above that, so that would be perfectly fine. Like I said, as long as it's defined somewhere, you're good. Okay. So I mentioned that I added two. This would have been the last problem, but I went ahead and I added two extra problems so that we would just get a little bit of extra practice, especially with the interpolation, because sometimes interpolating in those superheated tables, it's not as intuitive as the problem that we just did. So let's do a problem where that is not quite intuitive. All right. So here we've got a closed rigid tank. And so right away, just the fact that it says the closed rigid tank, I'm going to right away say, I'm going to say my volume is constant. And because my mass is constant, that also means that my specific volume is constant. So that's going to be really important for me for fixing my state. It's initially a saturated vapor at state 1, so my quality is 1, temperature is 200 degrees Celsius, and then it's heated to 240 degrees Celsius. And so I'm going to sketch it on a PV and a TV diagram. And yeah, it said determine the initial and final pressures. I mean, clearly I'm going to be accomplishing that on that PV diagram, so that's fine. I probably should have put A, B, C, D, P1, P2. Yeah. All right. So state 1, yeah, so it's a saturated vapor, so I need P1 and P2. So let's go ahead and get that guy. So P1 equals something. So at state 1, you know, clearly I've got a quality, so that means that it's saturated. And so I'm going to go to those saturated tables. I'm going to go to the ones that are organized by temperature. And at 200 degrees Celsius, well, the only possible pressure that I could be at is that 15.54 bar. So I guess that's my new A. And of course, for that PV TV diagram, I'm going to need the specific volume. So I'll go ahead and get this guy. So the quality is 1, so it's the V sub G at T1. You could plug it in that formula, get the same thing, but I've got a specific volume, 0.1274 meters cubed per kilogram. And so now that you've got that, because it's a rigid tank, that specific volume is constant. So now you've got your other property. Because once again, in order to fix your state, you need 2 of those 4 intensive properties: temperature, pressure, specific volume, or quality. And here, of course, we're assuming that the specific volume is the same as at state 1. And it's 0.1274. All right. So first place I'm going is my saturated tables, because I need to figure out what phase it's in. So I can see that, well, at 240 degrees Celsius, if it were going to be saturated, then the specific volume would have to be between your V sub F value, 0.0012291, and your V sub G value, and it's clearly above that, right? So my V2 is greater than the V sub G at T2. That tells me it's superheated. And so I need to get out of those tables, and I need to go to my superheated tables. So this would be really easy. Remember, those superheated tables are organized in blocks of pressure. And so normally I'd say, great, let me look for the block of pressure that corresponds to, you know, my pressure, but I don't have the pressure. And so what I need to do is, well, I've got my temperature and I've got my specific volume. It's still enough. I just kind of have to finagle. Finagle. All right, so 240 degrees Celsius, 0.1274 cubed per kilogram. So what I'm going to be doing is I'm going to be looking, I see I've got like, let's see. Let's do that. So I'm going to be looking like along those lines corresponding to 240 degrees. And what I'll see is that you know, I'm looking for something that's kind of close to that 0.1274. So here's a value a little bit above that. Here's a value a little bit below that. And so I can see based on that, well, I know my pressure is going to be between 15, and 20 bar. All right, so I'm going to interpolate for that information. So, oops. So you can see sort of at the bottom, I've come up with this little table to help us. And so I've organized it a little bit differently, but it doesn't matter. You can organize that table however you want to. So at 240 degrees Celsius, well, I have at 10 bar, I've got, oh, I'm sorry, at 15 bar, at 15 bar, my specific volume is 0.1483. And I think my head's in the way, and I'm sorry about that. And then at 20 bar and 240 degrees Celsius, my specific volume would be 0.1085. But my specific volume at 240 degrees Celsius is 0.1274. And so that's sort of like the table that I'm going to set up so I can interpolate. So if I do that, I ended up getting a value of 17.63. And that's...
When you say interpolate, what are you doing?
So remember, you're looking at each of these as data points, and you're saying that the line that connects them is linear. You're saying that there's a linear relationship between each of those things. So if you were to draw a line between each of those, like all three of them, or just between two, those lines would have the same slope. Okay, and so what you'll do is you'll say, well, the slope between that bottom one and the top one is, that would be your delta y. So P2 minus, let's say, 15 over 0.1274 minus 0.1483. That's the same as the slope between the middle one and the top one. So 20 minus 15 over 0.1085 minus 0.1483. And so if you solve for that P2, you should get 17.63.
Gotcha. Thank you.
Yeah. All right. So perfect. So I got my P2. Guess I'll box that. And then of course I need to draw things on a PV and TV diagram, so we'll do that now. I'm trying to keep like whatever I covered last in the window, but if I do need to scroll back up, please don't hesitate to ask me. All right, so this is not a constant pressure process. It was a constant volume process. That was right. So state 1 was right on that saturated vapor line, and then P2, or state 2, we found was in that superheated region. So what's this, just so we can kind of keep it straight, or kind of keep it reasonable. So 15.5 bar. And then state 2 is in that superheated region. That looks like it's straight up and down, and this is 17.63, and all of this is in bar. Of course, this guy is 0.1274 cube per kilogram. And we could do the same thing, our TV diagram. Okay, and the line is, the line of constant volume is still straight up and down. So this is 240 degrees Celsius. This was 200. 100 degrees Celsius, and of course this is that 0.1274 number. Okay. Right. So the important takeaway message here is when you interpolate, I would put, your own little table here, put your own table together, and that way it's organized the way that you're used to seeing it, right? For me, in my mind, as long as I can make it look consistent to myself, then everything sort of falls into place in my head. All right. We'll work another problem where we have to do something sort of similar. All right, so we've got water with a quality of 90% in a piston cylinder. It's heated at a constant pressure. So 90%, temperature 210 degrees Fahrenheit, constant pressure process to a temperature of 300 degrees Fahrenheit. And we're going to draw it on a TV diagram, which of course means that we need the temperature at each state, which we've got that, but we also need the specific volume at each state. So I need to find that specific volume first. So, of course, state 1, we got a quality, and then we've got a temperature. Here, might as well write it. P2 equals something. 2 is equal to 300 degrees Fahrenheit. So P2 is equal to P1, which we don't know yet. So we're going to find out. So at state 1, we've got a quality, so it has to be saturated, right? And so if I go to my tables at 210 degrees Fahrenheit, the only possible pressure that I could be at would be at 14.13 psi. And that's going to be important because I need that information over here. Right. So I know this because it's the saturation pressure at T1. And then of course I need my V1 as well. So I've got a quality, so I'm going to calculate everything with that quality. Okay. So I'm going to, of course, use the V sub F and the V sub G value for those guys. And it's in feet cubed per pound mass because we're in English units, so make sure you go to the appropriate tables. Otherwise, you're going to get yourself confused and waste time getting confused. Wouldn't be the first. I would prefer it. That doesn't happen to you. So V sub F 0.0167, V sub G 27.82. Perfect. So I've got 20. So state 1, like I said, was in that 2-phase region. We had a quality of 90%. So it's going to be kind of close to that saturated vapor line. And then of course, state 2 is out there in that superheated region. I'm going to clearly draw it, go straight across and then up in that superheated region. It's my V2, which I've got defined up here is 32.27 per pound mass. Of course, this is V1, 25.04. But if you just put V1 and V2 and you had it defined up here, that would be, of course, just fine. T1, 10. T2, 100. That's it. Okay, excellent. I was a little bit worried we wouldn't actually have time to finish all those, but that worked out fine. Can you show the math in getting V2, please? Yes, absolutely. So there was a question about the interpolation part of this. I'm going to put that in blue. So you're thinking of each of those lines as sort of a coordinate, and you're defining a slope between each of those coordinates. And you want to work, I always work from the bottom up. You just want to be consistent in how you define it. So you're trying to find V2. So delta y over delta x is your slope. So V2 minus minus, I'm sorry, I had just like 30.52 over 14.13 minus 14.17 equals, let's do 30.52 minus 44.99. So what I mean by working from the bottom to the top, right, it's 30.52 minus 44.99, not 44.99 minus 30.52. This would be 14.7 minus 10. So whatever that, when you solve for V2, you should get 32.27. And as long, if I see that I'm between those two values, I probably did everything correctly. Zoom in. I gotta, I'll be quiet. It's like, it's silent, so.
So for this test will be the practice exams and then just going over all the problems we've done in class and everything.
Yeah. You got 22 problems, and there's only so much variety that I can throw in there. This test, I really want to see, can you fix the state, right? Can you figure out what two independent intensive properties that you know, and from that information, can you fix the state? Figure out the other missing properties. And can you draw it on a TV and or a PV diagram? That's really what I'm looking for.
Okay.
Yeah. And so if you're comfortable with the problems that we've gone over in class, you've gone over the practice test, and that seems reasonable, I'm not planning on throwing in a curveball question. It's going to be phrased very similarly to the questions that we've gone over in class. If you want extra practice, there's, go check on your book, see if there should be example problems and stuff in there. But really, the best way to prepare is look at the class, look at the problems we've done in class, because they're, like I said, they're phrased the way that I'm going to ask them on the test.
Whenever we're doing the TV and PV diagrams, when like you're doing like the red dots to show like the changes in phase and everything, sometimes I might have just drawn it looking back to the last couple lessons, but there's a few times where like the first on the line, what is the reason for it being on the line? Is it like,
so
you know what I'm saying?
All right, so you'll put the dot under the dome if it's saturated and it's got a quality of somewhere between 0 and 1. If you've got a saturated liquid, which means that you've got a quality of 0, then it would be right here on that saturated liquid line. If you had something with a quality of 1, then it would be right there on that saturated vapor line. If it's superheat, then it's going to be, in the superheated region. Is that the question that you're asking?
Yeah.
Okay.
Yeah, that's what I was asking.
And there was a question about posting the video. It populates automatically on the YouTube playlist. So every lecture gets automatically posted there. So as soon as class is over, it's there. You don't have to. I think that's much more convenient anyway than having to log into Canvas and then look at the Zoom lecture,
All right, thank you.
Okay. All right. Yeah. All right. And once again, you probably got the email about that was really directed towards the 1220 section. I'm going to have a little bit extra office hours this afternoon. So if you do have some last minute questions, it's a good time to ask me. Otherwise, I'll see you guys on Monday. Okay. All right. Thank you.